So again, let me then thank. So thank you also for letting us know. Let me thank Hans again for the really kind invitation, and it's wonderful to be here. I'm looking forward to telling you about recent work from my team, but also from Ben Lennion's team in Innsbruck, and in collaboration with Nicolas Sanguard in now in Paris. So really kind of a big group effort, and we've been working on this topic about quantum interfaces for a long time. You heard also about kind of quantum interfaces in the previous talk. And in particular, I'd like to try to give you a sense today for the benefits of trapped ions for these kind of interfaces, in particular, because maybe trapped ions isn't something that you have so much of here in Innsbruck. You have many other quantum platforms here at the MCQST, and so maybe it's a bit of a different perspective. And I'll try to give you some motivation for that. I also want to try to give you a sense here. So our focus here is going to be about entanglement and on remote entanglement. And I know that everyone here knows all the wonderful things that you can do with entanglement, but just as a reminder, if this will work, let's see. Interesting. Try that again. As a reminder, so I want to just kind of think about why we think entanglement is interesting. And so on one hand, right, we know that it allows us to test very fundamental physical theories, like tests of violations of Bell inequalities. For example, last year's Nobel Prize. It also enables these whole set of new technologies for quantum computing, for quantum communication, for quantum sensing. And so we have the sense of entanglement as this wonderful resource that's both kind of very fundamental in a physical sense and applied at the same time. And today I really want to focus on this idea of entanglement over long distances, and in particular, why would we think that would be interesting to separate out the distance scales of, let's say, in the simplest sense, two objects that are entangled with each other. And so maybe fundamentally, we just find that strange, right? This is funny to think about. You have these two objects which might never have seen each other and could yet still be entangled. This idea of a really of a state that extends over long distances. And then we could be more precise about it. We can say that also there's these fundamental physical tests that rely on long distance. For example, if we want to violate Bell inequalities in a loophole-free way, then we're going to need long distances to do that. And for example, Harold Weinberger here in Munich and his group have been part of these kind of really landmark experiments. And then we can point out that distributed computing. So if you want to take two quantum computers or more quantum computers and link them together to build a more powerful computer, this will require or we presume that involves a kind of a physical separation where maybe you're taking advantage of the fact that you can build links between computers, which means you don't have to build such a complicated computer to start with. And I would point to the example that we saw at the end of Florian's talk previously, this idea about we saw these kind of two superconducting systems connected by a channel, and you could think of that as a way to build two superconducting-based quantum computers and link them together. And then we could think about distributed sensing, such as for networks of telescopes or on smaller scales as well. And then, of course, these ideas about secure communication, about provably secure communication based on quantum states, and on length scales here that are potentially worldwide. So here I want to show you with these kind of sense about why it might be interesting. Let me show you this map, this vision of a very European-based quantum internet. And this is coming, this concept is coming from a European consortium that my group is part of. And there's also a couple of participants here at MPQ and in Munich. So both Gerhard Rempe and Andreas Freisler, their teams are also part of this large consortium. And the vision here is about linking together quantum states. And so here we can think of these little glowing dots, right? If you look closer, they're sort of supposed to be little arrows with different colors, which is supposed to indicate some kind of an entangled state or a superposition state. So we can think about those as being places where you have local quantum computation, simulation, and sensing. And then we can think about these, lightning bolt kind of links between them as ways that you could distribute entangled quantum states. And so the big picture question here then becomes, how could we distribute this kind of entanglement efficiently and with high fidelity, potentially over long distances. So we're interested in a range of distance scales here. As I indicated before, for long distance networks, maybe this is particularly interesting for communication, but also this on shorter distance scales, these ideas about distributed computation and simulation. And so there's this vision of a hybrid network. I'm going to focus today here on trapped ions, but I'm not trying to convince you that the future is a story about ions talking only to ions. I think that the most compelling vision right now that we have is about linking together different kinds of systems, linking together ions with neutral atoms, with solid state platforms as well. And we'll kind of talk a little bit at the end about the potential to do that via, for example, telecom frequencies. So, I want to emphasize that currently the state of the art here is about linking together, 2 or 3 is about generation networks of 2 or 3 matter-based nodes. And people have generated now physical separations of entangled states of up to 35 kilometers. I actually updated that very recently based on a new paper from the Lucan group in a Boston area quantum network. So this is really work that's being advanced very quickly by many groups worldwide. But still, this kind of these ideas of just a couple of quantum nodes and scales of maybe a couple tens of kilometers at the state of the art, really impressive experiments, but still very far away from this vision of a continental scale network with many nodes that can do many different sophisticated things. And so I want to highlight that it's really an important and open question about whether we can bridge that link. It may be that we can't, but if we can't, it will be for interesting reasons. And so I think this is really the right time to try to see if we can bridge that link. Because it's not just about engineering, right? We're going to need significant advances in fundamental science. And an example I want to point towards here is that we've known how, on paper, to build quantum repeaters for now something like 25 years. There's beautiful descriptions for how to do it. Of course, they've gotten more sophisticated and more interesting from a theory perspective, but experimentally, it's really hard. And so there's a lot of really interesting and fundamental experimental challenges to overcome, but it's, as you know, it's a wonderful time to be working on quantum science. Right now, we have a lot of resources and opportunities that we didn't have just, say, 5 years ago. And so it's an exciting time to look at these questions. Let me summarize for you in one slide what this talk is about. It's a picture of our technical campus at the University of Innsbruck. This is a story about 2 different buildings on that campus. In each building, we have an ion trap. In each ion trap, we have a trapped ion. And the story is going to be that we entangle those 2 ions with each other. So that's the nutshell. And hopefully you'll stay awake to hear about some of the details. So I want to tell you about how the kind of 2 main ingredients that you can think about for putting together that story. And we're going to talk about ions and cavities as those 2 ingredients. And then I want to tell you in particular about trapped ions for quantum networks and some of their strengths, because you might be not familiar with trapped ions at all. And if you are, you might be familiar with them for quantum computing rather than for quantum networks. And then I'll come to this main result that we published in PRL this spring about entangling these 2 different ions in different buildings. And at the end, I want to discuss some prospects that we have for scaling up the system. So let's talk about these 2 different ingredients here. And the first ingredient is simply this idea of an ion trap. And so I want to sort of, in the sense of an overview, just show you a lot of pretty pictures of ion traps. And the message that I want you to get here is that they can look very, very different from one another. So I'm showing at the top some kind of earlier ion traps. And these first few ion traps are kind of larger scale things that you could hold in your hand if they weren't in a vacuum chamber. But also people are now using chip-based devices, both from NIST and actually these are both US traps from Sandia and NIST, but there are of course European traps as well. So the big picture is that all of these very different looking devices and very different sized platforms provide electromagnetic fields that provide a confining potential for charged particles, and here for atomic ions. And we'll talk a little bit more about that later, but the picture is just that we're bringing in electrodes to which we apply radio frequency fields that create confining potentials. So we're going to use these traps to confine an ion in one place in space. And then we're going to use another kind of a trap, an optical cavity, as a way to get light in that same place, because we're interested in this kind of an interface between light and matter, and in particular between a single photon and a single ion. And so you can think of, just in the simplest case, I think there's many people here in this audience who know quite a lot about optical cavities, but in this very simple picture, two highly reflective mirrors, light bouncing back and forth between them. And that's really going to allow us to confine this interaction between a single particle and a photon to a very small mode volume, and to boost the strength of that interaction. And so these ideas go back quite a while to these pioneering experiments, both with microwaves and with Rydberg atoms in Serge Harosh's group. And of course, Gerhard was part of early experiments with optical fields and atoms back in the days before we were trapping atoms in these kind of experiments, when they were even just traversing through a cavity, and now much more sophisticated experiments where the atoms are in fact trapped inside those cavities. So those are two pictures about kinds of neutral atoms, right? Rydberg atoms and the optical frequencies of non-Rydberg atoms, of more standard atoms. And more recently, these concepts about looking at the interaction of a quantized electromagnetic field with an atomic system have been extended to solid state systems, to atom-like systems. For example, superconducting qubits, like we heard about in the previous talk, interacting with microwave fields, but also solid state defect systems like nitrogen vacancy or silicon vacancy centers or quantum dots. So we have these two ingredients now, and here we go. And so I want to now talk about this idea of coming back to that first ingredient, to trapped ions, and talk about why they might be particularly suitable for quantum networks. So let me show you some more pretty pictures to start with. This is kind of a nicely lit up image of a vacuum chamber, to just remind you that this is something that takes place in ultra high vacuum with these kind of with these electrodes in the middle of that trap. And the key concept here for all of those traps that I showed you images of beforehand is that you've got 4 electrodes, here they're shown in gray, that you drive at radio frequency. And in fact, you can get away with grounding 2 of the electrodes and driving the other 2 at radio frequency. And that gives you a potential, or actually a pseudo potential, in 2 dimensions in the plane of the slide here. And then in the 3rd dimension, so we actually have a quadrupole mass filter. And then in the 3rd dimension, these are these brown electrodes. We apply DC fields to confine the particle in the 3rd dimension, and that gives us a trap. And then, right, we typically use either lasers or some combination of lasers and microwaves to manipulate both the electronic state of those ions and also the motional state of the ions, due to then the vibrational levels in that trap and the coupling of those vibrational levels to one another, because you can think of these ions as confined in the same potential. So, right, you can split out the confining potential into 3 dimensions. You can separate out, think of it as 3 different harmonic oscillators. If you're used to optical traps, these can be maybe about even 1,000,000 times deeper, something like 10 electron volts, megahertz type trap frequency. So that's maybe a little bit closer, not so far away from optical traps. So here's a pretty picture from Rainer Blatt's group in Innsbruck of many, many ions in a chain. And what are we looking at here? Actually, we're looking at fluorescence of those ions when the ions are being driven. In this case, at 397 nanometers, they're calcium ions, and they're fluorescing on a camera. So here in this picture, the spacing between the ions is about 5 microns. That's sort of a typical spacing. Yeah, just to give you a sense for this kind of image. There we go. So I want to tell you about these kind of give you a sense about the strengths of ions more broadly for quantum information processing. And the key aspects here are that they're highly isolated because they're in this ultra high vacuum system. And we have this kind of exquisite control over them from lasers or microwaves. And so some of the kind of the best numbers that I could show you, on one hand, if you use hyperfine qubits, so if you encode information in hyperfine atomic states here, you have essentially infinite T1 times because you're in 2 ground states. If you're interested in T2 times and coherence times, the best record numbers are over an hour for ytterbium ions, which have a magnetic field insensitive transition. Entangling gates, so if you're talking about let's entangle 2 ions with each other, typical times like hundreds of microseconds, but the record times were actually under a microsecond, something about 500 nanoseconds. And then, these very, very high fidelities for state preparation and single shot readout. So this is the faithfulness with which you can do that so like projected onto the ideal state. Kind of errors in that fourth 9 for preparing and single shot readout, and errors in the sixth 9 for single qubit gate operations. And again, 2 qubit fidelity, still very good, but now in that third 9. So really high fidelities for all of these things. But let's also keep in mind, that doing each of these things well is one story, and doing all of them well at the same time is another story. And I think, that's not a special story about ions, that's a story about whatever your favorite platform is, right? So in this experiment, the experiments I'm going to tell you about today, we do not have an infinite T1 time. We have a T1 time of about a second because we're using calcium ions and we are encoding information in a metastable state. It doesn't really affect these experiments. We're doing stuff on much shorter timescales. The T2 time here is about 30 milliseconds, although actually in one of the setups it's even about shorter because of magnetic field drift primarily because it's not a magnetic field intensive qubit. And here we didn't work too hard to improve to optimize our fidelities because we were sort of working hard to get other things right. So I think that's a big picture story. This is still proof of principle experiments that I'm describing to you. And in very sophisticated quantum computers and networks that we hope we have in the future, we're going to need to bring all these things together in one place. And that's going to be a very hard problem. I want to give you 2 examples of the state of the art here and about kind of 2 different kinds of systems. So on the left-hand side, if you want to be able to talk to each one of these little ions separately and entangle them, like to say, pick them out and say, I want to entangle ion 2 with ion 7, then people are working with maybe 20 or 30 ions for those experiments. On the other hand, you might not need that individual addressability if you want to be able to entangle all the ions with each other for simulation experiments and then just watch the whole system evolve. Then maybe 50 or more ions, people are working with those kind of numbers now. And a lot of the focus now in experiments more broadly is about error correction and about understanding how to kind of incorporate things like to incorporate error correction and to involve mid-circuit measurements as well. So gate operations on individual ions versus collective gate operations. So this is a slide that's all about a single node of a quantum network in that original vision I told you, right? It's about ions in a single trap. And their collective interactions, these gate operations that I tried to tell you are very high fidelity processes. This is involving their shared emotional modes in a confining potential. So the idea about entangling 2 ions in the same trap is about the fact that they see the same confining potential, but they have a Coulomb repulsion from one another. So what about this other question about building links between ions and distant nodes? Now they no longer see a shared confining potential. They no longer see a Coulomb interaction with each other. So how do we get these ions in different traps to talk to each other? And these kind of, this connection between remote ions was first realized in Chris Monroe's group, who was then at the University of Maryland, now at Duke University. And so starting actually with a paper back in 2004 where they first entangled a single ion with a photon, and then building onto in 2007, they first entangled some remote ions. And I wanted to use these examples from Monroe's group as to kind of step you through this concept of how you can entangle remote ions. In this case, it was ytterbium ions. And so here I've kind of copied 2 kind of little photographs of the traps they were using in their setup. And what you can think of is that each of these was a trap in a vacuum chamber. They were in the same lab, a couple of meters apart. And in one of the experiments, they had 2 atoms, 2 ions, and the other one, they had another ion. And we're really only worried now about 1 ion. So that's from their most recent experiment in 2015 on this topic, in where they had the highest efficiencies. And in one of these setups, in both setups, they're collecting light from a single ion. And you can see that they have some objective, which is a bit fancier than what we see here, but they're collecting as much light as possible and coupling it into an optical fiber. And so the key concept here is to start with this first step is about atom-photon entanglement. And the idea is that there's two different possible ways for the ion to decay. So you excite the ion, you bring it to an excited state, and then it's got two channels for spontaneous emission. And this is sketched here on the left-hand side. On the right-hand side, there's a sigma plus channel that brings us to a -1 state, which is a little black dot. And there's a sigma minus channel that brings us to this white dot, a +1 state. So we see that after the spontaneous emission, that we have this ion where the electronic state of the ion, minus or +1, is entangled with the polarization state, sigma plus or sigma minus. And maybe it might throw you off. Well, that's where did we get coherence from? But yeah, this is just because it's spontaneous emission. There's still a coherence in there that comes from the Clebsch-Gordons. We have a phase relationship between those two decay channels. So now all we had to do in each of these chambers was to bring the atom to an excited state, and it had two possible ways to decay. So we have ion-photon entanglement. Now the photons go in a second step to a beam splitter. This beam splitter erases information about which photon came from which ion. And then the third step is to detect both photons on a set of photomultiplier tubes in this experiment. They're after some polarizing beam splitters to split out polarization information. And the idea is that detection of two photons in particular states projects the ions into an entangled state. So if we assume here that we started with spin polarization entanglement, where we had one spin, let's say spin up, with correlating to a sigma plus photon, so some kind of polarization, with entangled with a spin down, which correlates to a sigma minus state. Then what we've detected is two different spin states. We've detected one spin being up, one spin being down, and that projects us into a state. Sorry, we detected one polarization being plus, one polarization being minus, and that projects us into a state where one spin is up, one spin is down, but we don't know which one is which, and so we're actually in a superposition of both of those states. The phase relationship here comes from which detector we detected the photons on, and so we can, based on which detectors, we can know whether that phase is minus or plus, right? There's we can detect two of these possible four Bell states. So very generally, this is not about ions, but very generally speaking, this is a method that's been used for many other quantum platforms, atoms, solid state qubits, like nitrogen vacancy centers or quantum dots. And generally speaking, this method, as Harold Weinfurter and colleagues showed several years ago, it can be used for detecting at most two of the four Bell states. So this is a heralding method where it's going to work 50% of the time, but you know with this heralded information that you detected two of the four Bell states, and the other times you detected two photons in the same polarization, and you ignore it and you go on and try again. Okay, so this is a story about how you entangle two remote ions, or in fact, actually any two spin systems that you could entangle with a polarization degree of freedom. And I just want to point out kind of state-of-the-art metrics here. So in these experiments from Chris Monroe's group that I told you about, fidelities here of the ion-photon entangled state with respect to a Bell state here of about 92%. So that's about saying, let's compare our density matrix from our experimental data with the target state. The fidelity of the ion-ion entangled state. So again, comparing the density matrix in your experiment with your target state of a maximally entangled state of two ions, a bit lower, but still highly entangled. The classical threshold here is 50%. And what was really special about this experiment from 2015 is that, to my knowledge, it was the first demonstration of remote entanglement faster than decoherence. So you can see that they're sort of entangling these systems about like 5 times more quickly than they can, than things are falling apart. And so I hope maybe that can convince you that that's really a necessary precondition for building anything more complicated. Because if you can't kind of connect two systems faster than you're kind of losing the coherence between them, then it doesn't practically really make sense to connect more and more of those systems together. And then since then, it's been demonstrated in one other system, I believe, in nitrogen vacancy centers in Ronald Hansen's group in Delft. More recently, in Oxford, in David Lucas's team there, using strontium ions rather than ytterbium, there have been higher fidelities demonstrated for ion-photon and ion-ion entanglement, and also faster entanglement rates, although the decoherence rate is also pretty high in those experiments. So here I want to actually shift gears a little bit because I've told you entirely about a process based on spontaneous emission. And I've also told you a story that didn't involve any cavities. But I told you that cavities were going to be our second ingredient. And we're now going to use cavities because we're going to try to look at this ion-photon interface instead from a perspective of a coherent interface. So this brings me to my third topic here, our work on entangling ions across the campus in Innsbruck. And let me show you this schematic of our experiment where you see little kind of pins, little needles above and below, and that's trying to indicate to you this kind of general structure of an ion trap, and this little green circle in the middle is showing an ion. And now we're going to put a cavity around that, and you see mirrors to the left and the right in the standing wave mode or the cavity in between. So what you should picture is that we're going to couple a trapped ion here to the mode of a high finesse optical cavity. And I'll describe to you here the kind of simplest version, which is a version based on a 3-level atomic system where we have 2 ground states and an excited state. The ground state on the right-hand side is actually a metastable state. It has a lifetime of about a second that I mentioned earlier in the context of this T1 time. So, right, if you're experts, those are the states are S and a P and a P3 halves and a D5 half state, but you can just think of it as a lambda type system for calcium-40. And so the key concept here is going to be a Raman process connecting the 2 states. But in contrast to the Raman processes that you might be familiar with involving 2 lasers that would connect, or 2 fields that would connect ground states to each other without exciting population, here we're going to use only 1 laser. In the second case on the right-hand side, this is going to be the vacuum field of the cavity. But we're going to tune these 2 into a very particular frequency relationship. In particular, we're going to match the frequency difference between the laser and the cavity to the frequency difference between the ion's electronic states. And that means that then when we turn on the laser, we can use that process to take the ion from the S state on the left and bring it into the D state on the right. So we pull a photon out of that laser field and we put a photon into the vacuum field of the cavity. And so we've generated a single photon in the cavity in this process. So now the ion is over here in the D5 half state. And if we want to tell the difference between which state the ion is in, then we have to introduce a 4th state into this system. It's a P1 half state. And so the point is that this 4th state on the left-hand side, this couples to the 1st state, the S state, but not to the state on the right, not to the final state, the D state. So if we introduce a laser at 397 nanometers on that transition, we'll see fluorescence. It's quite a strong decay rate of about 20 megahertz. So we'll see a lot of fluorescence, and that will tell us which state the ion is in. If we're on the D state, the laser doesn't couple, and so we don't see any fluorescence. And the final thing that we can do here is actually we can drive that coupling directly. It's a quadrufold transition. We can drive it directly with a titanium sapphire laser to manipulate that state. So I've kind of described to you this calcium-40 system, and in particular, what I've shown you is how we can generate a single photon from an ion coupled to an optical cavity. And so this is connecting to the story I told you earlier about ions and photons and generating single photons, but we still only have a single photon here. And what I'd like to kind of move towards is how we can generate entangled states. First, let me show you the actual experimental system that we've been using for some years. Here in the middle is the Paul trap, like the one you saw earlier, rotated now by 90 degrees. So these kind of electrodes here, just outside the electrodes, you see 2 mirrors, which are the cavity, and just outside those cavity mirrors, you see some lenses that are inside of the vacuum chamber. There's an image of an ion in the very center that we couple then to the standing wave of the cavity field. Here's again that illustration that I showed you about a single, a Raman process that generates a single photon. And what we're going to do now to generate an entangled state is to simply duplicate that process. So in this D5 halves state, it's actually a manifold that we can split out into 6 different Zeeman states. So we apply a magnetic field. We have 6 different states to choose from. We pick our 2 favorite states, and we couple our original S state to both of those 2 final states. So there's a Raman splitting here between those two final states. And that means that we're going to need a slightly different laser frequency to couple to the second state to match that Raman frequency difference. So we have two different laser fields. One takes us to the first state, the other takes us to the second state. And we pick out those states in such a way that the polarizations of the photons we generate are orthogonal to one another. And so we choose, in particular, we kind of can say that if we start in S, we can either go to a state that we call D, D 5/2 state, or it's the 5/2 spin state, Raman state, and we generate a horizontally polarized photon, or we go to the D prime state, the second state, and we generate a vertically polarized photon. And if we do this at the same time, we have, we can balance the probabilities to generate one kind of atomic state and one kind of polarization, or the other kind of atomic state and the other polarization. And I've written this down to here just to, to suggest this is a quantum state. So why do we get a phase relationship? Why won't this just be a mixed state? It's because those laser fields have a phase relationship with respect to one another. They actually come from the same laser. That is shifted by an AOM at two different frequencies. So because we introduce we have a phase relationship between these two Raman processes, we actually can generate an entangled state of these two final states. So what I've just described to you is an alternate way to entangle ions and photons, not via spontaneous emission, but instead via a Raman process. This is just data to tell you that we can entangle this state we can come very close to a maximally entangled state. So this is the kind of density matrix that you get from such entanglement. This is this density matrix. When you look at the projection onto a maximally entangled state, it's very close to 1. And what's really nice about this from kind of a perspective of applications is that you can tune the amplitude and phase of the entangled state because you can tune that via the laser that you use to drive the system. So if you're using spontaneous emission, you're restricted by the amplitudes and phases of your Eclipse-Gordon coefficients. But here we have a tunability that comes from the fact that we're driving it via a laser. We also can use that to shape the temporal shape of the photon that leaves the cavity. And what's really nice is that the photon leaves the cavity in a very well-defined mode, namely the cavity mode itself. So we could also, we went on actually in this several years ago to kind of use this experiment to entangle two ions with one another. That is, we put two ions in the same cavity, we entangled each ion with a photon, and then the photons that exited the cavity were entangled with one another, which we could verify in what's called a parity measurement. So we could use the parity of the ions to bound the entanglement between them. So what I've shown you so far is how we can entangle an ion with a photon in a cavity using a Raman process. And then I showed you that we could extend that to two ions in the same cavity. But I really wanted to tell you a story today about ions in different cavities. And again, that was the story about these two different buildings. This is really a collaboration that's now started some years ago, actually back even in 2015 with Ben Lanyon, who at the time was over at the Koki building here in Innsbruck. So different laboratory, but a very similar ion trap to the one I've described to you. It's a bit shinier, it's gold coated. That's supposed to be a way to reduce noise that comes from the electrodes, although both traps actually have quite low noise, are quite smooth. So they're actually or designed also to be very similar to one another, these two traps and these two cavities. And we can use both of those traps and cavities to entangle ions with photons. And so for a long time, we've had this goal. We, again, starting several years ago, this idea that we could try to entangle the two setups. And we had from the very beginning also a nice optical fiber, or actually two bundles of optical fibers linking the two buildings through the parking lot underneath them. And so, that was our plan. And so how do you do it? Well, we're going to do the same thing I've described to you. We're going to take those two photons and send them to a beam splitter because we need to erase that which way information about which photon came from which of our setups. And so let me point out here that it's really essential that these photons are indistinguishable from one another. And that's because if some characteristic of the photon, some temporal characteristic, frequency, spatial characteristic could tell us about where it came from, then that's a problem. Then we don't have this entanglement here. So we want to verify that the photons are in fact indistinguishable from each other. And so this is an early experiment that we did where we sent the 2 photons and we just looked at this histogram for when they arrived, so that you can think about this as a histogram that shows us about the shape of the wave packet. So as a function of time, looking at the probability that we get photon counts. And so here you see the 2 different nodes. A is the one on the left, B is the one on the right. And you see that they don't overlap perfectly, but they're sort of good enough for a first try. And you might also pay attention to the axes, and you see that we're getting more than twice as many, or than 10 times as many counts from node B. And that has to do with the detectors being closer to node B and with node B being more efficient. But that doesn't matter here. It doesn't, we don't need to match the efficiencies of the nodes, but we do need to match their temporal shape. That is like the probability for when a photon will arrive. And matching their temporal shape isn't actually enough because we also need to match their frequency characteristics. So not only temporal, but also we need spectral indistinguishability. And I'm sure many people here know that the way to look at this would be to look at so-called Hongo-Mendel interference, or the Hongo-Mendel effect. And this relies on the fact that we know that if we have indistinguishable photons, that they will bunch at the output of a beam splitter. They will leave the beam splitter together. And so if the photons are really indistinguishable, we should never see coincidences on opposite ports of a beam splitter. And so we're going to look at that here. And so for comparison, let's start with the blue data, which is photons that we've chosen not to be distinguishable. We've made their polarization orthogonal, so we know that we can tell the difference. And then we look at the difference in detection time between the 2 photons. And the key moment here is 0 difference in detection time when they should arrive at the same time. And in fact, that's actually the most probable time for them to arrive. And now we switch to the red data where they have parallel polarization. So we would hope that they're indistinguishable. And we see, in fact, that dip really going down here almost all the way to 0. Okay, so that gives us the confidence that we do have indistinguishability. And we can talk a little bit later about what's going on out in the wings. But the key point here is this dip at time t equals 0 that tells us that we have some indistinguishability. So now, yeah, indistinguishability. Yeah, okay, we can actually just talk right now about it, what's going on here. This is telling us, ideally, all the red data would be at 0 for the whole plot here. But as you get farther and farther away, that is, as the time between when you detected your first photon and when you detected your second photon increases, then there's a probability that you had spontaneous emission at the second ion that is due to an imperfect Raman process. There was some spontaneous emission event, and you could have detected it. So even if you didn't detect it, it's still a problem because the environment, the world, the universe knows which ion generated the first photon, and so we have this distinguishability. And so, yeah, not a perfect system, but still, again, enough for us to do a first experiment. So, it took us some time. We had to get the timing synchronized between the 2 labs. We had to get the frequencies synchronized between the 2 labs. And we had to make sure that the polarization of the fiber link between the 2 labs was well stabilized. And so many people put a lot of effort into that. And then we were ready to send photons to the same beam splitter and detect them on opposite ports. Let me remind you here that in the end, all we're asking is all a detection is of a measurement of the ions is my ion bright or is it dark? And that's actually all we can ever do is say it's bright or it's dark. It's in one state or the other. But we can rotate the basis in which we measure the ion with that 729 laser I showed you before, with that laser that rotates the state of those 2 ground states, that rotates the relative phase. And so that means that whenever we detect 2 photons, as I'm shown here, we just simply measure the ions, and we can choose which basis we measure the ions in. So to summarize, we measure the ions in 3 different bases, and we also can measure, and actually we have 2 different ions, so 3 bases for one ion, 3 bases for the other ion. That is, we can do 9 different kinds of measurements, and that lets us extract the joint density matrix that describes both ions, and that tells us everything we want to know about the ions. In particular, we can now calculate any of our favorite entanglement measures. So let me give you the results. Here's a picture of a density matrix. So what we see, first of all, is that all of the data, or not all of the data, most of the data is in those 4 middle entries. And that's where on the axes, we have either one ion is in D, or the second ion is in D prime, or the first one is in D prime, and the second one is in D. So this is telling us that the population is exactly where we want it to be. And as you may know, that's not enough. We not only need populations, but also coherences. And coherences is what you get from the phase information on the plot, the blue and the red. And so I don't think there's any, I certainly can't look at that plot and tell you, okay, I know what that is, but once you have that density matrix, you can then calculate its projection onto, say, their target state here, which was one of the 4 Bell states, the asymmetric one, up, down, minus, down, up. And here we get a fidelity with respect to that state of 82%, so well above the classical bound of 50%. And that was for one of our 4 Bell states. Here is the picture of detecting photons on opposite ports of that non-polarizing beam splitter. And let me just give you the other example, which is when we detect photons that came out the same port of the non-polarizing beam splitter. And that's going to make one of the symmetric Bell states, psi plus. And it's a very similar looking density matrix. The colors are different, and that means that the phases are different, and that's going to give you a pretty similar fidelity here, 88%. So this is the main result, to show that we're entangling these 2 ions in different labs that have never seen each other. We can think a little bit harder and kind of go into the details about it. And so I do want to mention to you that I'm showing you here a restricted set of the data, because I'm restricting the data here to cases in which the second photon arrived within a microsecond of the first photon. So we're choosing to look at, back to this plot about when the photons arrived. We're choosing to say, if the green photon arrived at one time, and we're looking in this, actually in this smaller window here of like 20, the first 22, I think, microseconds. After the first photon arrived, that the second photon arrived only a microsecond later. And I'm doing that because we want to kind of look at this best case of when we get the best density matrices. But we can look at all of the data. So if we accept longer differences in the arrival times of the photons, we still see a non-classical fidelity of our entangled state, but the fidelity as a function of this interval between the 2 photon arrival times, it goes down. And so what we have is this trade-off between the fidelity and the efficiency of this process. We can have, on one hand, just 3 events per minute for the high fidelity, or more like 3 events per second for the lower fidelity case. And so this trade-off, we understand it. Theoretically, we have a master equation model that can reproduce this experimental visibility. And in the end, it comes down to that story I showed you earlier about the fact that we sometimes off-resonantly excite the atom to an excited state, even though a Raman process should keep us out of the excited state. And so when we actually take that experimental data, we can use that experimental data to make predictions that allow us to understand and model this system very well. How would we get around that in the future if we want better entanglement, that is higher fidelity, more efficient? We know that we did a very bad job about stabilizing one of the cavity lengths. That was my cavity, and we should do it better, and we know how to do it better. There's also, those photons, they're not transform limited, and we know how to optimize the Raman processes. And you can think about doing things that are a little fancier, like encoding your state not just in one ion, but in multiple ions, and that would give you a stronger coupling to the cavity. And we also can be more efficient about the whole process, including how we cool the ions and how we detect them. So just to wrap up, let me just give you a few of the prospects for how we would go from this kind of system of 2 different quantum nodes that were entangling well above the classical limit, but still, not perfectly, to a more complex network, and a network over longer distances in the future. So the next number after 2 is 3. And we would certainly like to have a 3-node network. In my lab, my group, we've been working for several years on fiber-based cavities. And so this is what you see in the upper right-hand side here. This is a different experiment where this is also a Paul trap. It looks very different. It's a very squashed Paul trap. And then the cavity here now is on the tips of these 2 little optical fibers that come from the front and from the back of this picture. And so this is a miniaturized system that we hope we can use to scale up these kind of experiments in the future. And in particular, it should allow us to couple the atom to the cavity mode with a stronger coherent coupling rate, with a higher coupling rate. We recently have used it in some experiments to test the electric field noise models in ion traps. So we're able to kind of move around the distance between the mirrors and the ion. And this allows us to, matches very well with theory in terms of understanding the heating rate of the ions. As a function of let me go back here. So it allows us to analyze the heating rate as a function of the ion and fiber distance. And so this is kind of highlighting just a particular challenge in scaling up these systems, which is the idea of bringing dielectrics, which can have image charges very close to charged particles. And I want to broadly point out that understanding this kind of surface-related electric field noise and ion traps is going to be crucial not only for scaling up quantum networks, but also for quantum computers as we think about how to try to miniaturize these systems, and that means bringing them closer to surfaces. So it's a challenging problem, and a lot of people are working on it. Yeah, I showed you a link that was in real distance space between these labs, about 230 kilometers, and the for example, with Karl Weinfurter's group looking at an effective 33-kilometer distance between two experiments. So we could, for example, put a 50-kilometer link between these systems. Here we had photons at 854 nanometers, and that works just fine at kind of kilometer length scales, but it's not going to work for 50 kilometers. And there we're going to need to convert to telecom, where the 1/e length, so you lose kind of 1/e of your photons after about 22 kilometers. So that would work at telecom. And here's an example of work from Ben Lanian's group, my colleague's group in Innsbruck, where they've taken ions entangled with photons at 854 nanometers, converted them using nonlinear crystals, periodically poled lithium niobate, to convert the photon to 1550, and you still hold on to that entanglement. So that photon that you get after conversion is still entangled with the ion in a very high fidelity. So we've done that with one of those two systems, and our next step is to work on doing it with the other system so that we can link those photons via these converted photons at higher frequencies, at telecom frequencies. Right, so this is the main result I wanted to show you about today, that these two systems are entangled with each other. I've also described to you kind of more broadly that this ion-photon entanglement is a building block for this remote entanglement of the two systems. And I've tried to argue that cavities, while they're not necessary for these experiments, they do offer us some advantages, in particular efficient collection and control over coherent dynamics. The cost is certainly the experimental complexity, right? So building a cavity is challenging. Many people here know that, but it does have these nice advantages. And I've shown you recent experimental results where we detect two photons, and that heralds the remote entanglement of two ions. And we've characterized that remote entanglement via quantum state tomography. In the future, as I mentioned, we'd like to shift this work into the telecom regime, allowing us to span much longer distances. We'd also like to work with more ions. So I'm showing you experiments with one ion in each trap. But really, some of the most beautiful things you can do with trapped ions is when you have many of them in the same trap, and you can really take advantage of these high fidelity gate operations. So we'd really like to start entangling remote quantum processors with multiple ions in different traps in different locations. With that, let me show you the team from my group. So many of these people worked on this, in particular, the 5 people in the lower left, Simone Bayer, Dario Fioretto, Maria Galli, and Pepu, and Marcus Teller were the 5 kind of key people from my group working on this project. And then we had a wonderful team that we worked together with from Ikoki and also from the University of Innsbruck, led by Ben Lanian. And then the really wonderful theory support here from Basel and now at CAA, led by Nicolas Sanguard. I also want to mention that maybe about half of the people in my group work on different experiments, on quantum optomechanics experiments, and I'm happy to talk to you about that separately some other time. So with that, let me thank you very much.
Thank you, Tracy, for sharing your impressive results. Questions? Just wait a second. So we switch on the ceiling microphones, and then you're audible globally.
Should I go?
Yeah, you go.
I was wondering what kind of modifications, configuration one have to do to try and just catch the photon from another atom instead of doing the heralding.
Right, so there would be a separate way that you could build such a network, so which would be not involving ion-photon entanglement, but instead you map the quantum state coherently from an ion or an atom to a photon, send it to the other system, and absorb it in that system. And Gerhard's group worked on this more than 10 years ago here, and did those experiments here with neutral atoms. So in our we have done half of that, so kind of mapping a state from an ion to a photon. And we've looked at the other half about absorbing it from the photon and mapping it onto the ion. So that's so I would really like to do more of those experiments, and I think they're a lot of fun. With the ions, they're challenging because of the coherent coupling rate. So because we're not operating here in a strong coupling regime, but in some kind of an intermediate regime. And so for that, you really need that coherent transfer in both directions. So I think we might be able to do some initial experiments with the cavities that I showed you, but the real nice candidate for that is the fiber cavity that I showed you at the end, which will have the stronger coherent coupling rate.
Thanks.
Yeah, thanks for the nice talk. I was interested to learn more about the fiber stabilization, which you mentioned. So you mentioned it took some time. So how do you do that? Do you do single mode polarization non-maintaining fibers, or do you have polarization maintaining fibers which you control? So
yeah, so thanks for the question. So these are polarization maintaining fibers. And so essentially we interrupt our experiments about every 20 minutes. So we find that the stability is good enough for maybe 10 or 20 minutes, but then it's drifting too much. So after taking data for say 20 minutes, then we send states from one node to the other. We send known states from one node to the other. We analyze the output polarization, and we figure out what rotation we need to make to correct for the drifts. And so then this takes a couple of minutes. We rotate some wave plates to correct for those drifts, and then we keep going. Does that
okay? Yeah, because I was wondering, because non-polarization maintaining fibers seem sometimes to be more stable in terms of the polarization stability, and it's yeah.
Yeah, I think that's right. And so I think it also depends. Like I think in that case, you really need to do a good. So I think if you've done a good job of isolating them, like putting them in sand or something, right? Then they will actually be that will be a better choice. But in this case, it was out of our control because they were already installed.
Yeah, thanks, Tracy. I was wondering, first of all, comparing neutral atoms and ions, you already commented on a few things. Maybe you can say a bit more advantages or disadvantages using those. One thing that seems to be hard with the ions is like you have all this electromagnetic environment around the dielectrics, right? And I think in the picture of your fiber tip, you could see that it seemed to have like metallic sleeves around the fiber, or was I right?
Yeah, exactly. You're right. Yeah.
So can you comment a little bit on that, how much you have to take care of that and how much that is a problem?
Yeah, so I think that you're highlighting kind of the big challenge with ions compared to neutral atoms is dealing with that environment. And then that kind of, so yeah, here with the metal sleeves, it's also because we're sort of incorporating it's like a end cap electrode plus a mirror in one.
Oh.
So we've put the mirrors inside of the end cap electrodes, but we also hope that in doing that, we're shielding, it's providing the shielding, and essentially we believe that, the charges on the mirrors should just act as a different voltage on your end cap electrode. So somehow.
Is that stable, or do you have to compensate for that, like continuously, or?
It turns out that in our case, it's stable.
Okay.
Yeah, so that seems relatively stable. But yeah, one problem is about these charges on dielectrics. And another problem with the dielectrics is maybe more fundamental, is that any dielectrics near an ion trap, there's going to be, so there's motion of the ion at the secular frequency, then which is generating electric field, which is dissipated in the dielectric. Because of the fluctuation dissipation theorem, this dissipation of the dielectric, corresponds to fluctuations of the electric field, which will heat up the ion. So also in general, bringing ions close to dielectrics will lead to heating up the ion. So that's a second problem. Yeah, and then that connects to the fact that, right, so if you look at Gerhardt's cavities, which are just much smaller, it's just, it's still very hard to build those cavities, but it's easier than doing that with an ion to bring those mirrors much closer. Yeah, and then I would say, pointing to the strengths, then, having that trapping potential that's so much deeper, then lets you, do experiments with one and the same ion for many hours, and which then lets you position that ion very precisely in the cavity and just leave it there, and lets you be very aggressive about measuring it and not worry that it's going to leave. So that kind of set of things that come with that very deep path.
You mentioned cavity stabilization, cavity lag stabilization. Do you do that actively, So with piezos, and how do you deal with the stray fields from piezos?
Yeah, so maybe I'll just point like other people online. Let me try to do it with this thing. So okay, I just can't get that level of precision. I'm sorry. Okay, so here and here, there's little piezo stacks. So shear mode piezo stacks that we use to actively stabilize the cavity length at a wavelength that the ion, doesn't matter for the ion. In one of the cases, it's 785 nanometers, in the other case, 808 nanometers. So because you need to stabilize the cavity length to something like picometers or even better. And so yeah, so active feedback there.
And what about the stray electric fields from the piezos?
Right. So this design of the holders was intended to shield that, and in general it does. Although we also saw that it matters. So the piezo has a electrode above and below, and it matters which one of those electrodes. Like we keep the one above near ground, and we apply the high voltage to the below one because we see the problems if we do it the other way around.
Maybe I have a question also in this respect. So you're carefully controlling all or adapting all your parameters, system parameters, in order to create entanglement. In this endeavor, did you encounter any indications that you used this already as a sensor for some external noise, stimulus, magnetic fields, kind of on the scale of your experiment, which spans over hundreds of meters?
Okay, so not just as a local sensor, but
just a correlated sensor, basically spanning over this length scales. So
yeah, so I think we certainly we haven't done the analysis that of any of that aspect of it, but I think that the fact is that you get a different, you will have a different magnetic field environment in both places, and we're taking steps to match that, right? So we have to balance the state so that in fact we compensate for that. And so if you wanted to, you could work backwards from what you're doing to balance the splitting of the states and try to find out about differences in the magnetic fields. I'm not sure that's particularly useful, but yeah, that would go in that direction.
So Tracy, you showed these sort of entangling rates of like about a hertz, I think, but it's sort of like 1 per second scale. So over the sort of 5-year time scale, like how much do you think you can bump up that number, and what are the steps that you would want to take?
Right. So I would say like kind of a factor of 1,000 is what you would sort of hope for. I mean, I think when we kind of work through the numbers about where we think we're losing, where we think we're losing efficiency. The main points would be, well, in general, in the experimental sequence, there was a lot of buffer time just because we didn't try to optimize, say, detection time, or we just matched the two systems, and we didn't bother to try to come up with an optimal, or we put a lot of effort into just getting the two systems to talk to each other, but not using optimal sequences in both places. So sort of very kind of mundane aspects like that, and then maybe using kind of better kind of state-of-the-art techniques for cooling more efficiently and so on. But then I would also, I think at some point you have to, we think that we would move to say multiple ions for this kind of boost in efficiency in the coupling rate. So I think we think on this kind of 5-year time scale, we could maybe get a factor of 1,000 with essentially with these systems. And I think that's kind of the limit of like these physical systems that I'm showing you. And the hope would be for systems like fiber cavities. But again, they have their own experimental challenges. But I think that we need to get more than a factor of 1,000. I think it needs to be a different platform.
And you're thinking of having several ions talking to the same optical cavity?
Yeah.
So are there questions from our online audience? Please just unmute yourself and ask. Seems not to be the case. More questions here from the floor? And let's thank Tracy again. Thank you.